Okay, so last time we started to talk about the equilibrium of particle. If you have a particle, bunch of force applying on that, so how we are doing the equilibrium compared to sigma effect, sigma effect. We did an example last time. We are going to do another example, and we move to 3D. Next example we're going to do that. If you have in a box or plate here, and it's go up there, there, connected to still like that. And then there's a force on me there. And then you know that this is going to be theta, the angle of the and so we have this and support most so each rope that we know the rope for each of the rope the maximum is 10 kilonewtons. If the if the tension in any of those rope becomes more than 10 kilonewton, it will break. So, and this is 200 kilogram. So,
10 kilotons is a fair amount.
yeah.
10 kilonewton, not tons. 10 kilotons. I don't think that's a thing, but
So now the thing is asking me, I'm holding it there, and I release it, until at some point it will break. What's the point that, or not holding it. At what theta? What's the minimum theta before it breaks?
so like we're pulling, like if we were to let go of the string, the weight would start like swaying. So that circle is just the spot where our string is attached. It's not actually like a pivot point or anything, it's just where it's being held. Okay.
If I start to so if the AB is always horizontal, what's the smallest angle before one of the ropes break? You get the problem? So I can play with that, and at some point it will break and it will fall down. What's the minimum theta that before it breaks and falls down? So if I have that, the first thing I'm gonna draw the free body diagram for that point. And this is what they call it, A, B. It's an A, B, C, and D. If I go ahead and draw a free body diagram for point A, so at point A, I'm gonna have the force that's going for F or AB. That's the force that we are applying. Probably FAB. And then I have two tensions there, and there's a tension here, which is gonna be T A D, and there's gonna be tension here, T A C. So if I go ahead and find their components, just remember, so we're gonna find their component first, so it's gonna be AC. Remember, if this is a theta, this is a theta, this is gonna be theta. You know why?
It's the same thing.
No. The theta is a theta.
Yeah.
That these two are parallel, and one pass through two parallel lines. So it's gonna have the same name. So it's gonna be theta there. So it's gonna be TAC cosine theta that's going this way. And then we have TAC sine theta going up. And the other two. Now if I go ahead and write the sigma, so I put basically the free body diagram, draw the free body diagram, put all the forces there, then find the components of the forces in the x and y direction, and then write sigma fx is 0, sigma fy is 0. So let's just start with sigma fx 0. What would give me the sigma fx 0? If I write the sigma fx, I have the FAB minus TAC cosine theta will be 0. Right? So FAB would be TAC cosine theta. Right?
Why? Like, why does that work? So the FAB. Oh, because they're canceling each other out because the objects aren't. Gotcha. All right.
So if I have that equation, what can I say about the FAB and TAC?
They're opposites. No, they're the same.
They're opposite. Cosine theta, what's the range of cosine theta?
1 to -1.
1 to -1. In this case, it's probably between 0 and 1.
Yeah.
Okay, because this is between 0 and 90, so it's between 0 and 1. So I know that this is the cosine theta is less than 1. If the cosine theta is less than 1, which one of these two are larger? TAC or FAB?
TAC. Yeah, TAC.
So TAC is larger, so in that case we know that the TAC is larger than the FAB. Just and then let's have that there. Then the sigma Fy is 0. So that's the sigma Fx. Then sigma Fy is 0. If I write the sigma Fy, what do I have in the Fy direction?
TAC sine theta and then TAD.
TAC sine theta minus TAD would be 0. How much is the T80?
How much is it? Just 200?
It's a weight.
Yeah.
T80, so it's gonna be 200 times 9.84.
1962.
So TAD, I'm gonna rewrite that, so it's gonna be TAC sine theta minus TAD, which is gonna be 9.81 times 200 will be 0.
Oh,
And how much you said it is?
1962.
1962. Yeah.
so that would be 1.9 kilonewtons, right? And
Okay. Now between AC and AD, which one reached the 10 kilonewton first?
see what, because the force on AD isn't changing. Because the amount of weight it's holding will never change. But the cosine and sine for AC will change over time, changing the amount of stress in the string, or tension on the string. Will.
So here, what we have, it says that AC is larger than the AB. Always. So it means that the AC reaches the 10 kilonewton first. Because if the AB wants to reach the 10 kilonewton first, it means that it is already reached the 10 kilonewton
That would be a lot simpler.
and it's already broken. Right? So that one should be always, that one is the one that, what to say? That is the one that should be 10 kilonewton. So if this 10 kilonewton, I can put it here, I can get, so this is the one should get 10 kilonewton, so I can go ahead and put it in that equation. So I can go ahead and say, hey, now, first is the 1, this is 1, and this is 2. And then second 1 and 2, I would say that TAC should be 10 kilonewton. And then I will go ahead and say, okay, 10 kilonewton. Zero, and therefore the theta would be
11.3.
11 quarters. So it's going to be sine inverse of 1962 divided by 3 times 10 to the 3, which is going to be 11.3 degrees. So remember, whenever you have a problem that, okay, which one would be, you have a couple of rows and it asks you which one would break first, you have to find out which one would be maxed first. Okay? You have to find which row max first, and when you find that rope, that specific rope, put the tension in that rope equal to the maximum it can handle. Because that's the rope that's gonna break first. So we set that rope is we set it to the max, and then from there we calculate everything else. We can go back and calculate it because we have we have the theta, we have the TAC, we can go back and calculate the FAB if you want, or another values as well. So one more time, if you have assume three ropes, and they said which one, what's the maximum angle or what's the maximum weight that you can put on this system. Go and see which rope has the maximum tension and set the maximum tension in that rope equal to the maximum tension it can handle, and then from there calculate everything else. Got it? So this part that I was looking for, that was that I want to find out which of these two ropes would be maxed first, or which one would you break first, and then set the limit in that. Any question about that? And from there, as I said, if you want to find the FAB, you can go ahead and say, okay, the FAB is AC cosine theta, which is 10 times 10 to the 3 times cosine 11.3, which will, I don't know how much it will give you. So you can calculate it. You have that?
Yeah, it's like 9.81 kilonewtons.
9.81.
Yeah, it's the exact same as gravity.
Something like
10 times gravity. 100,000 times.
Next, we're going to look at the equilibrium in 3D. And let's see. Okay, leave the board. Very good.
I'm good.
So I'm going to just put all the 3D together, try to put them together. So here it was up to here is what if we have the two, but let's look at what we have with 3D. Okay. So equilibrium particle. In 3D. Similar to what we have in the 2D was like that. If I want to have the particle, if there's a particle and a bunch of force applying on that, in the 3D format, as well as the 3D space. As well as 3D. The only thing is that if they want to be in equilibrium, sigma f should be 0. And if I go ahead and write that sigma f0 in the Cartesian format, it will be sigma fx I sigma fyj sigma fzk, it should be 0. And then all the forces in the I direction, all the forces in the J direction, all the forces in the K direction should cancel each other. So basically I have to have sigma fx0, sigma fy0, and sigma fz0 in order to have an equilibrium in the 3D format. In the 2D, I would say, okay, I should have the sigma fx0, the sigma fy0. When 3D, so I have to have all of them to be 0.
So they can't just cancel each other out, they have to be 0.
If they cancel, no, because this is along the x, this is along the y, this is along the z. They cannot cancel each other. Everything along the x should cancel each other.
Yeah.
Everything along the y should cancel each other. Everything along. So you might, when it is 0, it's like that either you don't have any component in that direction, or if you have, when you add them together, there should be 0.
Yep.
So for the procedure to solve the problem in 3D format would be, I want to say, so the first step, draw the free body diagram. First step, draw free body diagram. The second step, I put it as a separate step, but it's actually part of the first step. Apply all the active and reactive forces on the body. The next step is that, remember in 2D, what would we have done after this one? In 2D, after we draw the forces, we will find a component in the x and y direction. In the 3D, we don't do that. We are not going to find a component in the x and y and z direction, and the reason is that it's not easy to do that. So instead of doing that, we are writing each force in the Cartesian form. So when you get to this point, just write all the forces in Cartesian form. When you have all the forces in Cartesian format, in 2D, what will be done? In 2D, you said, okay, you find a component along the x and along the y, then you cancel all along the x, cancel all along the y. Sigma fx0, sigma fy0. Here, instead, we are going to write him as a vector. Just write the vector equilibrium equation. In other words, write sigma f is equal to 0 as a vector format. Next step, rearrange that equation, whatever you come up with, rearrange it into this. Rearrange. Zero. As in other words, put all the I component together, put all the J component together, put all the K component together. So when you write it like that, you have ijk plus ijk minus ijk, but each vector has its own ijk. The next step is just go put all the i's together, all the j's together, all the k together. When you get into that point, the last step is just now solve sigma fx0, sigma fy0, sigma fz0. Any question? We will do that in the example to see how it works out. Any question about it right now? Next, the next thing that I want to show you is that you had it, but I'm gonna repeat again the force vector because I'm asking you this one. This is probably the most important one. Write all the forces in Cartesian form. This one. So how we do that, or how to find the force vector. So we need to find the force vector for that purpose. Okay, remember, assume I have an x, y, z setting. There's 2 point A, B. And so the point A has a x, a, y at A, and z at A. And point B is a x at B, y at B, z at point B. And then assume there's a force along the point AB. This is the F that we want to find. So in order to find that, we have to go ahead and you have to find the position vector, which was RAB, and then the unit vector, UAB. So, remember what was the RAB? The position vector. minus first one. Second one minus first one. So it's gonna be xb minus xa I. yb minus ya j. Z at b minus z at a k. And the magnitude of that is b minus xa squared, yb minus ya squared, b minus za squared, and the square root of that. Now, what was the UAB? Remember? UAB is RAB divided by RAB, or UAB is cosine alpha I, cosine beta j, cosine gamma k. Either one, either this one or the other, depends on what we have. If you have the angle, this is the one you use. If you have the coordinate x, y, z, this is the one you use. And then at the end, FAB is the magnitude of FAB times UAB.
How is FAB equal to FAB plus the UAB? Times the UAB. That final equation doesn't make sense to me.
It was the magnitude, remember, times the unit vector. For example, if the force is in the x direction, it's this magnitude times I.
Okay.
So it's always the magnitude times the unit vector in that direction. If you go back when we discussed the position vector, we talk about it.
Yeah, I forget. I wasn't looking properly at the symbols above the F and the U and all that. Just show that they're vectors.
So you have to do this for almost any these steps. You have to do it for almost any force. Remember the third steps. Write all the forces in Cartesian format. This is how we write it in Cartesian format. Question? So, these things, this is third step. Sometimes, I mean, usually when we are dealing with the problems, we might have a case that is easier. So if I go ahead and say, if I have an x, y, z again like this, and let's have some force on that and see what we have. For example, by having F1 these four forces in Cartesian. So look at here, this is the general form for any forces. But if the forces are along the axis, it's usually easier because we already know the unit vector along x, y, and z. So for example, for the F1, I can write it for the F1. So the magnitude of F1 along the x is just F1, correct? The magnitude of F1 along this is F1. I. How much is the magnitude of F1 along the y? So it's going to be 0. So it's going to be 0 j. How much is it along the k? Or along the z?
0.
It's going to be also 0. So it's going to be 0 k. Or you can simply write it as F1i. Similarly for F2, it's going to be F2 doesn't have anything along the x and z, so it's going to be 0i plus F2j plus 0k, so it's going to be F2. Okay. F3 doesn't have anything along the x or y. Everything is going to be along the z. So it's going to be 0i plus 0j plus F3k, or just simply F3k. F4, look at the F4. Look at F4. F4 doesn't have anything along the x, doesn't have anything along the y, but it is negative along the z. So it's going to be 0i, 0j, minus F4k. So it's going to be 0i, 0j, minus F4k. This is going to be, or simply minus F4k. The last one, the F4, what's the example for the F4? Good example for the F4.
Like something that would normally look like a 4 on a graph.
Gravity.
Weight.
Yeah, wait.
So weight is always, when we want to write it in this notation, weight would be like that. Negative weight k. Negative or minus magnitude of the weight k. So if you are given the weight, you can find it like this, go through these steps, but it's just easier to find it like that. So if you have a force that is completely 3D, this is how you find it in Cartesian. If you have a force that is along the x, y, or z, this is how you will find it. So these two are just this step, write all the forces in Cartesian. Question? let's look at an example. So we have x, y, z. They're going to be so there's going to be points. I'm going to have okay. If you have something like that, you want to find the forces in the cables, AC and AD. Cable in the AC and AD, and deformation in the AB. So I want to find force in the AC, force in the AD, and the deformation the AB. So here there's one thing about this problem is that if you look at the forces, in this case, all the forces are in one of the planes. So for example, the DA is in XY plane. The AC is in the XZ plane. And the AB is just on the Y. So there is no force that's actually, they are all 3D, but they are in the plane, they are not somewhere in, for example, completely 3D. It helps us. We can still solve it the way that I said that, but we can do it in the easier way. So if I go ahead and say, okay, I'm gonna draw that. Okay. That'll be Y. X. And Z. And then I'm gonna draw the forces that I have. So the forces that I have for the AC is going to be TAC. Then I have the AD. I have 90 here, and I have F, A, B. I write all my forces like that. There. The direction that I chose for the AC and AD, why I chose those directions? The direction for the AC and AD.
Are the angles the same or opposites?
I mean the sense, not the direction, but the sense of that. Why not the other way? Because the rope only can withstand tension, right? The rope cannot tolerate the pressure. If I pull it that down, the only way that these two ropes are going to be in tension if they're like that. If I put the force the other way, it means that I'm pressuring the rope, so it's not going to do it. So that's why they're that way. So now I'm gonna find the value of them on the XYZ direction. Look at here, I told you in the procedure that go and write all the forces in Cartesian. Why I'm not gonna do that here? Because I actually can find them on the XYZ. If I couldn't find them on XYZ, I had to write it in Cartesian. But here I can. So if this is 30 degrees, it's 30, I'm gonna write them one by one and the Cartesian format. So how much is this? It's gonna be TAD cosine 30. And this is gonna be TAD sine 30. Agree? Yep. What about here? What is this? Here, look at here first. If this is theta, how much is the cosine theta? How much cosine theta if this is theta?
4 over 5.
Cosine is going to be 4 over 5, and sine theta would be 3 over 5. So now I can go ahead and say this is theta, and so this is going to be TAC cosine theta. This is going to be TAC sine theta. So now what happened? Now I have all the forces on the x and y and z direction. Right? All the forces are in x, y, z direction. So what should I do? Just sigma fx0, sigma fy0, sigma fz0. If I want to have the equilibrium, I'll write sigma fx would be 0. If I write a sigma fx0, it will give me FAB minus TAD cosine 30 will be 0. If I write Fy0, sigma Fy 0, I would have the TAC sine theta minus 90 would be 0. And if I write the sigma Fz0, sorry, that was the x, I made a mistake. And the fx, what do we have here? TAD, TAD sine 30 minus TAC sine theta would be 0. On the y, we have FAB minus TAD cosine 30 would be 0. And on the z, we have TAC sine theta minus 90 would be 0. So I have 3 equations, 3 unknown. But this one is a little bit easier because I can go ahead and here from the last one, we can say, okay, from here I can find the TAC, right? I can say that TAC is 90 divided by sine theta, which is 90 divided by how much of sine theta? 3/5. How much is the TAC? then if I set it as 1, 2, and 3, then I can put TAC in the 1, use equation 1, TAC is 150, so I can say that TAD sine 30 minus 150 cosine theta. No, it was, what was the cosine theta? 4, 5. 0, therefore TAD would be 150 times 4 divided by 5 divided by sine 30. Should comes out, if I have everything right, it comes out as 240 pounds. And then I can have the equation 2 FAB minus TAD, which is 240 times cosine 30, 0, so FAB 240 sine 30 comes out as 208 pounds. 8 pounds. Now, how much is the deformation in the AB? So deformation in the AB, we know that in the for the spring, F is K delta X or delta L. Changing the length. So FAB is KAB delta L in the AB. So it's going to be 208 pounds. Going to be, how much is that? Is it 500? That's delta L. So delta L would be 480 by 500. Foot. So it's going to be 0.41. That's how much that spring will be stretched for compressed. So that's how much that the spring will be stretched. 0.4. Any question about